In this video, I want to discuss two solutions to heteroskedasticity. These are not the only solutions because the solutions might depend on the cause. So, for example, if the relationship is not linear and you assume a linear relationship, the solution, of course, is to linearize the relationship. Maybe you shouldn't have used x, but you should have used x squared as an independent variable. But here I want to talk about sort of more generic forms of heteroskedasticity. So the first solution is called generalized least squares. And it's generalized because it can deal with more types of variance. The special case of this is now the constant variance. And we can use generalized least squares when we can come up with some kind of transformation, some value that explains the heteroskedasticity, and so that we can divide the variances by this quantity. For example, if I know that my data set contains averages, so imagine I have data on every province in a country, and I look at average income in each of these provinces as one of my variables. This average is a mean, is calculated for each province separately. Will actually have a different variance because the population size will differ, or my sample size will differ in each province. And so for each calculation of the mean, I will have a different variance depending on the sample size. And then if I then use those means in a regression where the provinces are the unit of analysis, I actually have different variances for each of those variables because of how I calculated the mean. So I can correct for that because I know the exact cause. I know the sample sizes. I know exactly how I calculated the mean. I know how this creates extra variance. I can correct for that. So generalized least squares in general means correcting your variance estimates instead of this constant variance sigma squared for each observation based on some known cause of the heteroskedasticity. So there are some cases where this is closely related, where the cause is not so precisely known, but where we can estimate separate variances for separate cases. For example, we might assume that the variance will be different for different subgroups in the data, and we estimate separate variances for each of the subgroups. Or we think that the variance will be correlated with x, and we can explain how it will be correlated with x, and we can estimate the coefficient for the correlation between the variance and the x variables. Or maybe there is a correlation with some other variables that are not in the model, but we know that these are variables relevant for explaining the different variances in the error term. Or we might say that there are some more complicated. I talked earlier about shocks that then lead to subsequent shocks in the data. So you can think of stock trading, for example, and the price of a stock might be moving relatively stable, and then there is a big shock because there's some major investor suddenly buying a lot, and then there will be suddenly a lot of trading in this stock, and it might go radically up and down and then calm down again. So the variance will be temporarily high and then normalize over time. So that is what the ARCH model, the autoregressive conditional heteroskedasticity model, tries to estimate, how the variance for a given period of time might be temporarily high. So these are all forms of estimated generalized least squares. We will not discuss them in any further detail beyond this slide in this course. It's just for you to know that when you know there is a particular reason for the variance to differ, because it's correlated with firm size, because it's correlated with shocks in the system, because it's correlated because certain groups are different from other groups, and so forth, then perhaps there is a model available that specifically deals with that type of heteroskedasticity. There's also one sort of more general solution, and some colleagues even recommend to always use this instead of regular OLS estimators for standard errors, which is called wide heteroskedasticity consistent covariance matrices. So HCCM in short. So this is an estimator for the variance of beta hat that instead of assuming a constant variance of all the errors for all observations, tries to approximate this by allowing for a different variance for each of the observations. And the most basic version of this is quite a simple logic, which is if I assume that the error term is 0 on average, then perhaps the best, so we assume that this is on average 0, and in fact with OLS it will be by definition 0, yeah, so the residuals are always going to be 0. Maybe one good estimate for the variance of the residual, a good estimate for the variance of an error for any particular observation might be to take the residual and then square it. Yeah. So the residual is the distance from 0 of that particular observation, 0 being you're on the regression line, and then the residual is your deviation from that regression line. And a variance is a squared distance from the mean. So if your regression line is the mean and you take this residual and you square that distance, you have an estimate of the variance. So in other words, the estimator for the variance of the error for a particular term is the squared residual of that particular term. And then you get then you can make a new diagonal matrix that you plug in there instead of omega, and instead of this that we did in earlier slides, where simply on every point on the diagonal we take the squared residual. So it's a diagonal matrix that still assumes no autocorrelation. And we tend to call this HC0 because it's sort of the first HCCM model. Now, but there is a problem with this estimator, and that goes back to the head matrix that we discussed before. So we had a head matrix, which is the projection matrix, projecting y on the space defined by x. And we said that the variance of the residual is sigma squared times 1 minus the head matrix, or 1 minus the leverage of a particular observation. And so because the leverage changes for each of the observations, that variance is not the same as sigma squared. So the variance of the residuals is not the same thing as the variance of the errors. And we know that even in the case where the real errors are homoscedastic, the variance of the residuals is an underestimate of the variance of the error terms in nature. And moreover, when the errors are homoscedastic, the residuals are not. So in a given sample, in a fixed sample size, you will not get exactly homoscedastic residuals, even if in the population there are homoscedastic errors. And the variance that is estimated this way, if you take the square of the residuals, you have an estimator for that population variance of the error, but it is an underestimate. So it's biased. Now it is consistent, which means that as the sample size gets larger and larger, these estimates become better and better. But for a fixed sample size, it is going to be biased. And it turns out that if the sample size is not all that big, like a normal sample, then this bias can actually be quite large. So this is not such a great estimator for the variance of the error. Now, and if we say that the estimator for the by looking at the squared residuals is not a perfect estimator because of this projection matrix and the variance of the errors being the product of the variance of the error term in nature and 1 minus this head, the leverage for each observation, then maybe dividing by 1 minus the head matrix might fix this, right? We know what is the cause of this deviation, then we can also correct for it. So HC2 in this example does exactly that. It takes the squared residuals, but then divides by 1 minus the leverage to correct for that difference between the variance of the residuals and the variance of the errors, sigma squared. So HC0, 1, 2, and 3, they're all different variations. They have in common that they are all somewhat biased. They have in common that as the sample size grows larger and larger and larger, they all converge to the same thing. So if the sample size is sufficiently large, these 4 different estimators of the standard errors will give you the exact same results. But the normal sample is not sufficiently large, and they will differ. So they have done simulations what happens in smaller sample sizes, and then it turns out that this third option, HC3, the fourth option, HC3, is the one that in a small sample gives you the best effects. Yeah? So through simulation, they figured out that they're all wrong, they're all biased estimates of the variance covariance matrix, but HC3 is the least so. And all of them are consistent, so all of them converge to the correct answer as long as the sample size grows and grows. So in R there is a package, the car library, which can be used to calculate these different HCCM matrices. So here's the code to calculate the standard errors manually. You can look at the summary of the LM command and see what the standard errors are in the normal calculation. You can then use the HCCM function to calculate a variance covariance matrix based on White's heteroskedasticity consistent covariance estimate. And then look at the square root of the diagonal of the variance covariance matrix, which are the standard errors, and then see how they differ. As an aside, but something I do not want to delve into here, but at the end of this course we get to simulation and Bootstrap. One alternative way of dealing with heteroskedasticity might be to derive your standard errors not from some matrix algebra, but by running the simulation many times, the estimation many times, every time on a different sample, where, and this is a kind of an unusual trick, and I will elaborate much more on that later in the course. A Bootstrap sample is a sample out of your sample that is the same size as your sample, but not the same observations. So you take a random set of your sample, and in that random set are the same number of observations as the original sample, but the same observation might be occurring 2, 3, 4, 5 times, and therefore other observations might be left out. So it's taking a random sample with replacement. You take your sample, you take one observation out, you put it back, you take one out, you put it back, you take one out, and then you check which ones you took out. So you end up with a sample size that's the same, but not identical observations, because some are duplicated and some are left out. And then on that new sample you estimate the model, and then you repeat this process hundreds, thousands of times. Each time you estimate the model, and each time you look at the beta coefficients, and as it happens the distribution of the beta coefficients across these Bootstrap samples will be an estimate of the sampling distribution, and you can therefore look at the standard deviation of this to have an estimate of the standard error. But this is really a little bit too much at this stage in the course, and we will discuss this more later. For the homework, you will be using HCCM to calculate heteroskedasticity consistent covariance matrices.